In the following two lectures, we will talk about two techniques to strengthen model formulations. One can be applied a priori. This is pre-solving. The other one is applied while solving the model. These are cutting planes. We are going to start with cuts. Little warning, this might be one of the densest lectures of this whole summer school. In the beginning, we will quickly review the idea of the general cutting plane method. Then, we will talk about individual groups of cutting planes, sorted into two main categories. The first are generic, matrix-based cuts, like Gomory cuts. The other are problem-specific cuts. Problem-specific here refers to particular combinatorial optimization problems, but such problems that we find as a structure in almost every MIP. So these cuts are still generally applicable. With all those cuts at hand, the question comes up which of them to use. This will be the topic of the final part, cut selection.
This lecture is connected to the follow-up lecture on pre-solving. The motivation for cuts and pre-solving is that the original MIP formulation can almost always be improved by the solver. For example, it might be reduced by removing variables and constraints, resulting in less data to process. Or it might tighten the relaxation, such that the continuous optimum is closer to the integer optimum. As mentioned in the modeling session, having the LP relaxation close to the set of integer solutions is a preferable characteristic of a model. There are two main techniques for doing so. The first of them, which is also the first to be applied in a solver, is pre-solving. It consists of logic reductions that are conducted before starting the main search. The second one is cutting planes, in which new valid constraints are generated and added to the MIP formulation in order to tighten the search space. This technique is performed at the root node, after solving the LP relaxation, as well as at the local nodes during the search. Cutting will be the topic of this lecture. There are three main principles that occur in many places within cutting and pre-solving. Rounding tries to exploit integrality, in particular by using that integer multiples of integer variables take integer values. The principle of lifting explores that fixing a variable at a bound might imply redundancy or infeasibility of a constraint, even if the fixed variable is not part of the named constraint. The third one is disjunction, which says that a binary variable must take one of two values. If some reduction holds in both cases, even if it is for different arguments, it will hold in all cases. This lecture is about different ways to generate cuts. Within our MIP Solver Flowchart, cutting plane generation creates its own little loop. Inside a node, in particular the root node, the solver will call cutting plane generation multiple times, each time reoptimizing the LP enhanced by the cuts added in the last rounds. It might also remove cuts from previous rounds, if they are no longer tight. The cutting plane method is based on the observation that the convex hull of all integer solutions is a polytope, at least for bounded integer variables. Recall how the general cutting plane method works. First, we compute an optimal solution of the LP relaxation. Next, we check whether this is integer feasible. If this is not the case, we find an inequality which is valid for all integer solutions, but violated by the current LP optimum. We add this to the LP. We repeat with the now further restricted working problem. We solve the working problem again. Check whether this is an integer solution. That's not the case. Again, we find an inequality. That is valid for the set of feasible IP solutions, and that's violated by our optimal LP solution. We add this inequality to our formulation, and we repeat. We solve again, and now we get lucky. We find an LP solution which is integer feasible, and this is an optimal solution of the integer program. There are many ways of generating cutting planes for integer programs, and they can roughly be separated into two categories. On the one hand, there are general or matrix-based cuts, which take only the MIP constraint matrix as an input and compute valid inequalities for this. On the other hand, there are combinatorial, or problem-specific cuts, which exploit some structures that are present in many, but not necessarily in all, mixed integer problems. Moreover, we could further divide the general cuts into those that work on the original matrix formulation and those that work on the tableau-based form provided by the simplex method. In particular, Gomory cuts fall into this latter category. As you saw, cutting plane generation works in rounds. The method solves the LP, then some old cuts might be removed. Next, new cutting planes are generated for the new LP optimum by one of the algorithms shown on the previous slide. Then the cuts are filtered, selected and finally added to system of inequalities. The terms filtering and selection are related to each other, but they mean slightly different things. Cut filtering is a decision about a single cut, cut selection is a decision about a set of cuts. More precisely, filtering typically consists in determining that a particular cut is not suitable for the problem at hand, whereas cut selection consists in choosing which of the filtered cuts will actually be added. The latter step has two motivations. First, some cuts might have desirable characteristics if considered on their own but might not work well together. Second, there might be working limits of how many cuts to add, which forces the algorithm to only select the most promising ones. The root node of a MIP search typically features a heavy cutting plane loop. Often MIP solvers do about 20 rounds of cuts, sometimes up to 100. Locally, there are only few cut rounds, like 1 or 2, if at all. Local cutting is typically not called at every node of the tree search. Let's first talk about matrix-based cuts. As a quick recap, Gomory cuts consider each inequality in the basic representation of the LP and split it up by putting the integer parts on the left side and the fractional parts on the right side. Then it can be argued that the right-hand side is less than 1, while the left-hand needs to be integer. This implies that the right-hand side is not only less than 1, but less than or equal to 0 for any integer feasible solution. This insight can be formulated as an inequality that is violated by the current LP solution. This means that Gomory cutting planes are directly read from the simplex tableau. Chvátal-Gomory cuts are loosely related to Gomory cuts. Chvátal-Gomory cuts work on the original matrix. They are only defined for pure integer problems. The method considers non-negative multipliers lambda and uses them to compute a weighted sum of the rows, in a fashion similar to the Farkas lemma or the definition of the dual LP. Taking a conic combination, that is a non-negative weighted sum of valid inequalities, gives again a valid inequality. This valid inequality will be redundant for the original system. Chvátal-Gomory cuts seek to make it cut off parts of the LP relaxation by using rounding arguments. Two steps of rounding are performed. First, the left-hand side is rounded down. This is because for non-negative variables and non-negative multipliers, the rounded down left-hand side is less equal the original quantity. Hence, this is a relaxation of the original aggregation. Second, the right-hand side is rounded to the next smaller integer. This is a strengthening of the relaxed inequality from the previous step. The hope is that this is even stronger than the original aggregation and cuts off parts of the LP relaxation. However, rounding down the right-hand side will not cut off any integer solution. For integer vectors, the left side is integer. Hence, for integer solutions, the inequality stays valid, even if the right-hand side is rounded down. To conclude, the Chvátal-Gomory method is able to generate valid inequalities. However, it is not immediately clear how to choose lambda such that it separates the current LP solution from the set of integer points. Unlike for Gomory cuts, there is no closed analytic formula. Different aggregation heuristics are used to search for a suitable lambda vector. To reduce their search space, it can be proved that the space of multipliers to generate these cuts can be restricted to the interval 0-1. In particular, there's the important special case of all components of lambda being either 0 or 1/2. These cuts, called 0-1/2 cuts, are obtained by summing up only some of the constraints weighted with 1/2 and have been described in the mid and late 90s. For this special class of Chvátal-Gomory cuts, there are efficient algorithms to find out whether there's any violated 0-1/2 cuts and which one is the most violated. Just as an observation, it can be proved that many important sets of facet-defining inequalities for special combinatorial problems can be expressed as 0-1/2 cuts. This indicates that this is a meaningful class of cutting planes to try and explore. A generalization of 0-1/2 cuts are mod k cuts, which use 1/k to mod k/k as possible values for the multipliers. Hence, a 0-1/2 cut is a mod 2 cut. Let's talk about mixed integer rounding now. We describe the idea of mixed integer rounding for the special case where there are only two variables, one continuous, one integer, and the coefficients of the variables are 1. We consider what is called a mixed integer set. This is the feasible region of a mixed integer program with two variables, one integer and the other continuous, and only one constraint that connects the two, x less than or equal to the continuous variable, plus a right-hand side value b, which we assume to be fractional. Moreover, the continuous variable is required to be non-negative, the bounds of the integer do not really matter. This is the most basic form of a mixed integer program. In the pictures, the set of feasible solutions is marked as bold black lines. This is the mixed integer set. The convex hull of the mixed integer set can be seen as a blue polyhedron in the upper left picture. As you can see, already in this case, the one inequality plus the variable bound do not suffice to describe the convex hull of the feasible solutions. If you take the LP relaxation, it consists of the blue polyhedron plus the little red triangle. We will show how to find an inequality to cut off that triangle. As you can see, the boundary of inequality 1 intersects the x-axis at x equals b. Mixed integer rounding is based on a disjunctive argument. If an inequality is valid for two disjoint sets, it will also be valid for the union of the two sets. Here, these two sets are defined by a split on the fractional value b. The disjunction that is applied is either x greater than or equal to be rounded up, or x less than or equal to be rounded down. Of course, this has to hold for any feasible solution of the MIP, simply because x must be integer. Next, we generate an inequality that is valid for both parts of the disjunction, but violated by the fractional point 0b. Consider the MIR inequality as it is given on the slide. We show two different ways to construct this inequality, one for each part of the disjunction. The first one involves the condition x greater or equal be rounded up, which we call inequality 3. The other involves the condition x less equal be rounded down. This we call inequality 4. As you can check for yourself, adding up the inequalities 1 and 3 multiplied by plus b minus b rounded down, gives the MIR inequality. Of course, since 1 and 3 are the only two valid inequalities describing the upper part of the disjunction, a positive sum of them is, again, a valid inequality for this upper part. The same thing can be done for the inequalities 2 and 4, with slightly different scalars. Again, we obtain the same MIR inequality. Since inequality 2 and 4 are valid for the lower part, their positive sum will be valid for this part as well. We now found an inequality which is both valid for the lower part and the upper part, hence it is also valid for the union of the two. The MIR inequality, as depicted in the picture, can be added to the general formulation and will cut off the fractional vertex. For this very simple example, it turns out that the original formulation plus one MIR inequality are enough to describe the convex hull of the set of integer feasible solutions. As a final remark, it is also geometrically clear that the MIR inequality can be constructed in the given way. It goes through both the intersection point of 1 and 3 and the intersection point of 2 and 4, and its normal vector is both in the conic hull of the normal vectors of 1 and 3 and the normal vectors of 2 and 4. Hence, there must be non-negative multipliers to combine either set of inequalities to the MIR inequality. This argumentation can be extended to general mixed knapsack sets, which are the sum of scalars times positive integer variables and a single continuous variable. This also covers the more general case that there are multiple continuous variables, since for the argumentation to follow, they could just be aggregated into one single continuous. The so-called general MIR inequality is, as you can see, very similar to the two-variable case. The right-hand side value is rounded down and the continuous variable is scaled by a factor, which depends on the fractionality. We will not show the proof of correctness here, it is a generalization of the argument for the two-variable case. Unlike in the two-variable case, the general MIR inequality will not suffice to describe the convex hull of the mixed integer set. Other, stronger, inequalities might exist, which can be derived in a similar fashion. These are the so-called C-MIR inequalities. The C-MIR procedure, where C stands for complemented, is a heuristic way of deriving stronger MIR inequalities. It first divides the whole inequality by some positive delta, then complements some of the integers by replacing xj by uj minus xj bar, the complemented variable. For the special case of a binary, the complement is just 1 minus x. Hence, the complement of a binary is 0 when the binary is 1 and the other way around. Let's look at an example. Consider a mixed integer knapsack constraint x1 plus 4 x2 less equal 11 over 2 plus s. There are two integer variables and one continuous, and the right-hand side is fractional. We will show how different valid inequalities can be derived from this. Let's first consider the general MIR inequality. It is derived by applying the standard mixed integer rounding procedure of rounding down the right-hand side and dividing the continuous variable by 1 minus the fractionality. To apply the C-MIR procedure, one could, for example, take the decision of dividing this whole constraint by 4. This seems like a reasonable choice since 4 is the largest coefficient. Also, let us complement one of the two variables, as a heuristic choice. Since the integers are bounded by 2, the variable is equal to 2 minus its complement. Applying the scaling and the complement gives an inequality which is equivalent to the original constraint. Both have the same solution set, one is just a reformulation of the other. It is only now that we apply mixed integer rounding to this reformulated inequality. This gives a different MIR inequality than for the original constraint. We can substitute the complemented variable back to get an expression in the original variables. It is not clear a priori which of the two inequalities is stronger. If this procedure is used to produce cutting planes for a MIP, it depends on the solution that we try to cut off which one seems more favorable. In practice, the C-MIR separation procedure has been described by Marchand and Woolsey, who provided an efficient implementation of it. The method applies the MIR procedure to each mixed integer constraint in the problem. In their paper, they describe possible heuristic choices of which variables to complement and which deltas to use for scaling. Their procedure complements variables whose LP values are closer to the upper bound. Then, they try scaling by various deltas, but at most 4 times the number of integer variables in the constraint. For each coefficient, delta is chosen as an integer multiple of this coefficient, using the first 4 powers of 2 as multipliers. Again, this is a heuristic choice that works well in practice. Then, the procedure applies the MIR formula for each such scaled constraint. Next, it simply checks whether there is a violated cut in the set of MIR inequalities for the various different scalings, and chooses the most violated cut for each original constraint. At this point, it tries to obtain a larger violation by complementing additional or fewer variables one by one. Finally, if no violated cut is found in this way, it applies something like lifting, that is adding other constraint to the current constraint, such that one of the continuous variables is cancelled. Note 2 things. First, for such a procedure, there are various working limits in place, to not get out of hands for MIPS with many constraints, individual long constraints or constraints with all different coefficients. Second, the last step could also have been a first preprocessing step. Indeed, there are various different ways how to aggregate different mixed integer constraints in order to get an aggregated constraint that is most promising to derive strong cuts from. Intersection cuts are generated from the simplex tableau, just like Gomory cuts. The nice thing about intersection cuts is that they create a connection between cutting and branching. Assume we are given a fractional solution, and we apply an arbitrary disjunction on it. Typically, this is just a split on the fractional variables, but it could also be any other affine sum of the integers, just like in branching on general disjunctions. Remember the simplex algorithm? We visualized y pivoting from one basis to another corresponded to moving along the edge of a polyhedron. This defines a set of rays that are pointed in the current vertex solution and whose direction vectors are defined by the distance vector of the old and the new vertex solution. These rays define a simplicial cone. Notice the connection to the term simplex algorithm. This simplicial cone can be intersected with the boundary set of the disjunction that we consider. The hyperplane through these points is a valid cut for the underlying MIP. Look at the picture. Assume we try to separate the fractional red point. We consider a disjunction on the x variable, indicated by the dark shaded area, the split set. From the simplex tableau, we compute the two red rays. Next, we compute the intersection of the red rays with the boundary of the split set. This gives us 2 points. The hyperplane through these 2 points is the intersection cut. The important bit for this to be correct is that the split set does not contain any integer point in its interior. Such a set is also called lattice-free. Together with simple disjunctions, various generalizations to more general lattice-free sets have been suggested. The last general cutting planes in this presentation are lift and project cuts. They are intersection cuts but computed from an infeasible LP solution. The first cut, depicted on the left, is generated from the feasible LP solution V1, hence from a feasible basis. The intersection cut that we get from V1 is shown as cut 1. Let us go a step back in the dual simplex algorithm and consider an infeasible basis solution of the LP. This will still correspond to the intersection of n constraints and variable bounds, but one which violates another bound or constraint. This could, for example, be V2 in the picture. As you see, we will get a stronger cut from V2. This process can be iterated and cut 3 from the infeasible vertex V3 will be even stronger. This procedure delivers strong cuts when the new constraint which is pivoted into the infeasible basis is facet defining and the defined facet intersects with the split set. As the geometrical interpretation, this can be realized by performing a sequence of infeasible pivots on the original LP.
Quiz time! So, let's go. First question. Mixed integer rounding cuts. A. Rely on a disjunctive argument. Or B. Are less powerful than mixed integer Gomory cuts. Or C. Require the solution of an auxiliary AP. Second question. 0-1/2 cuts work A. On a graph structure. B. On the original constraint matrix. Or C. On the simplex tableau. Third question. In MIP solvers, cut generation is typically applied A. Only at the root node, B. Aggressively at the root and moderately at some tree nodes, or C. The same way at all nodes. Little time to think about the answers. And we switch to the solution in 3, 2, 1. There we are. First question was, mixed integer rounding cuts rely on a disjunctive argument. 0-1/2 cuts work on the original constraint matrix. And in MIP solvers, cut generation is typically applied aggressively at the root and moderately at some tree nodes. So, next we will talk about problem-specific cuts. Rather, about cuts for specific problem structures like networks or stable sets that can be found in many MIPs.
Let's start with cuts for the 0-1 knapsack problem. Consider the feasible set of a knapsack problem, that is the set of 0-1 variables satisfying a single constraint. This knapsack constraint is given by the sum of the variables multiplied by non-negative integer coefficients less than or equal to a non-negative integer right-hand side. We introduce the notion of a cover of a knapsack constraint. A cover is a subset of the variables, such that the sum of the corresponding coefficients in the constraints is strictly greater than the right-hand side. A cover is said to be minimal if the removal of any element from it makes this set not a cover anymore. From this, we can derive the notion of a minimal cover inequality. Such an inequality expresses that in any integer feasible solution to the knapsack constraint, at most C-1 variables from a minimal knapsack cover can be used. This follows from the definition of a minimal cover. Putting all items into the knapsack would violate the constraint, hence it is a cover. Putting all but one, no matter which, is feasible. This is minimality. The knapsack cover inequality expresses this. Consider the knapsack constraint on the slide. A cover can be constructed by taking, for example, the whole set of variables, since the sum of all the coefficients is clearly larger than 8. A minimal cover is given by the set 2, 3 and 4. Indeed, by removing one of these three variables, we obtain a set which is not a cover anymore. Finally, the last line states the minimal cover inequality. Suppose the inequality in this example defines the feasible set of a mixed integer program, whose objective is to maximize the function, say, 1/2 times x2, plus x3, plus x4. Then the solution given by 2/3, 1 and 1 would be feasible and optimal for the LP relaxation. However, it would violate the minimal cover inequality, since the sum of these three values is 2 plus 2/3. Cover inequalities can be further strengthened by lifting, hence by adding further variables to the inequality. For our example, this could mean that we try to incorporate the variable x1 into the cover cut. This corresponds to the question, is there any alpha 1, such that adding alpha 1 times x1 to the cuts is still a valid inequality for the set of feasible solutions. This can be found out, again, by applying a disjunctive argument. In this case, we want to lift one single binary variable, hence with value either 0 or 1. In the easy case in which xi equals 0, the inequality is certainly valid for any possible alpha I, since what we are left with is the same cover of before. This means we only need to consider the case where this variable is equal to 1. What happens in the next line is that we compute the maximum sum that our cover variables can achieve when the variable that we try to lift is fixed to 1 and the knapsack condition is still fulfilled. This is what the maximum in this line expresses. If this value is less than the right-hand side of the cover inequality, then we have found a feasible non-zero coefficient for the lifted variable. For our concrete example, trying to lift x1, we just plug in x1 with value 1 into the knapsack constraint. This means the remaining capacity on the right-hand side of the knapsack reduces to 3. Then, we ask what is the maximum of x2, plus x3, plus x4, under this constraint. This is 1. This means once that x1 is fixed to 1, we can get at most one variable of the cover into the knapsack. This means that alpha 1 can be chosen to any value that's less than or equal to 1. In particular, fixing alpha to 1, the lifted cover inequality x1 plus x2 plus x3 plus x4 less than or equal to 2 is a valid inequality. As you can verify, when x1 is 0, this gives our original cover inequality, and if x1 is 1, it implies that only one more of these variables fits into the knapsack. Let us do a little exercise. Get pen and paper and try to find a lifted knapsack cover cut for the knapsack problem on the slide. Proceed in the following steps. First, try to figure out what the optimal solution of the LP relaxation of the given problem will be. You should not provide a strict proof of optimality, but try to think about how you can maximize the objective when you are allowed to use fractional solution values. Next, can you find a knapsack cover that involves the variable with a non-zero solution value? State the corresponding knapsack cover cut and check whether it cuts off the LP solution. Next, try to find out whether you can lift another variable into this cut. Compute the maximal lifting coefficient and state the final cut. We will reveal the solution in 3 steps, making a 5 seconds pause between each step. Probably, you want to double-check the definitions by looking into the 2 slides that are linked in the video description. Pause the video now to solve the first part. x4 does not give any value, so it will be 0 in the LP optimum. x1 and x2 have the best cost-weight ratio and both fit into the knapsack together, so they will be 1. This leaves 4/7 for x3 to reach the capacity of the knapsack. 5 seconds pause. One, 2, 3 is a cover since the sum of the coefficients of x1, x2 and x3 exceeds the capacity, but none of the 2 elementary subsums does. Consequently, x1 plus x2 plus x3 is a valid inequality and it cuts off the LP optimum. Congratulations! You computed your first knapsack cover cut. 5 seconds pause. But we can go even further and lift x4 into this. If we fix x4 to 1, no other item will fit into the knapsack. This means that the cover cut that we just computed would have a slack of 2, and hence we can lift x4 with a coefficient of 2. This is the logic behind the lifting formula that we just learned. Our final lifted knapsack cover cuts is x1 plus x2 plus x3 plus 2x4 less equal to. Be again reminded that the typical application in a MIP solver is not a pure knapsack problem like here, but knapsack constraints being part of a big problem. The same arguments can still be applied. Let's now talk about the stable set problem. Given a graph, a stable set is a set of non-adjacent vertices. That is, none of the vertices are connected by any edge. In the example here, the yellow vertices form a stable set, since there's no edge between any pair of them. Like for all combinatorial optimization problems, this set can also be described as a polytope, called the stable set polytope of the graph. Therefore, we use 0, 1 vectors, whose components correspond to the vertices of the graph. Each component of such a vector indicates whether the corresponding vertex is in the stable set or not. The stable set polytope is defined as the convex hull of all such vectors which satisfy the requirement that the sum of two variables is at most 1, if the corresponding vertices form an edge in the graph. Hence, the inequalities force the stable set to include at most one of the two endpoints of any edge of the graph. However, to really describe the convex hull of these points, some additional inequalities are necessary, precisely the so-called clique inequalities. A clique is a set of pairwise adjacent vertices. In other words, the opposite of a stable set. In the example here, the red vertices form a clique, since all of them are pairwise connected by edges. Clearly, given a clique, at most one of the vertices of this clique can be in a stable set. Hence, a clique inequality, defined as the sum of all variables in a clique less than or equal to 1, is a valid inequality for the stable set polytope. Now, where does this occur in integer programming? Well, of course, we might have such a stable set structure encoded in the matrix. But we might also use this notion more generally, by considering what we call the clique graph. A clique graph is a data structure that MIP solvers maintain. It has one node for each binary variable and one for each complement of a binary variable. The edges are defined by each pair of variables that cannot have value 1 simultaneously in any feasible MIP solution. So those could, for example, come from assignment constraints. Those could come from two elementary knapsack covers, as we just saw, or from constraints such as x1 plus x2 plus x3, greater than or equal to 2. This means that no two of these variables can be 0 at the same time, if they are all binary. For the complemented variables, we can add an edge to the clique graph. Finally, cliques can also be detected in probing, as we will see in the pre-solving presentation. Hence, each feasible MIP solution has to fulfill all these conditions about the binary variables that have been discovered from the constraint matrix, from cutting planes, from pre-solving, and so on. This means that the assignment of the binary variables that are 1 in a feasible MIP solution corresponds to a stable set in the clique graph, because this graph is defined by binaries that must not be 1 at the same time. This means that the stable set polytope of the conflict graph is a relaxation of the MIP's feasible region. Hence, each clique that can be found in the conflict graph defines a valid inequality of the stable set polytope of the clique graph and therefrom also for the underlying MIP. The separation algorithm for these so-called clique cuts tries to find a maximum violated clique in the clique graph, essentially by a greedy search. Finally, let's talk about implied bound cuts. Assume we are given a continuous variable with upper bound y less than or equal to u. Assume further that we have a binary variable that implies a new stricter bound on y, when it is fixed to one of its two possible values. For example, we might have that x fixed to 0 implies y less than or equal to u bar, which is a new upper bound for y. Then, we can lift the x variable into the bounding constraint, and obtain what is called an implied bound cut. An important special case is the one in which u bar equals 0. So, if x equals 0, then y is forced to 0, as well. If x equals 1, then just the standard bound applies. As an example, consider the integer program in which we want to maximize y1 minus y2 minus x. Here, x is binary, while the two y's are continuous, y1 bounded by 5. Observe that, fixing x to 0, y1 and y2 would be also fixed to 0. The LP optimum of this small MIP is y1 equals 5, y2 equals 0, x equals 1/2, and, as you can see, the implied bound cut, y1 less than or equal to 5x, cuts off the LP optimum. To generate implied bound cuts, the bound implications must first be detected. This happens globally in pre-solving, where they are stored in the implication graph that you have already seen for heuristics. We can also use probing to detect local implied bounds at every node where we want to generate cuts. You saw that there are manifold possibilities to generate cutting planes. More often than not, the case might occur that we could add more cuts than what would be good for the solution process. Let's therefore talk about how to choose a few good cuts from a big selection. So, how many cuts should be generated for a relaxation solution? Of course, only one cut will already be sufficient to provide a new relaxation solution, but it will be expensive to solve the relaxation again and again for each single new cut that is added. However, adding as many cuts as possible is not advisable either. First of all, the relaxation solution needs to be cut off only once, thus a few cuts, which all accomplish this goal, might be sufficient. Moreover, each cut increases the size of the model, making the subsequent LP solve slower. Finally, cutting plane separators themselves might be expensive. Hence, finding a good balance here is really important. In practice, this means doing multiple rounds with a limited number of cuts per round, and replacing old cuts when new, better ones are found. Moreover, we choose carefully which cuts complement each other nicely. A good cut should be efficient, which means that the distance of the hyperplane to the LP solution should be as large as possible. If this is the case, the cut cuts deep into the polyhedron. This is a soft criterion. We usually require that minimum efficacy is met, and will sort the other cuts by the efficacy, such that when working limits apply, only the best ones survive. Moreover, cutting planes should be orthogonal to each other, such that they cut off different parts of the polyhedron, and they should be not exactly parallel to the objective, since this would directly induce primal and dual degeneracy. In contrast, if they are similar, but not parallel to the objective, cuts can be expected to trigger progress in the dual bound, which is good. Finally, a good cut should be sparse, only containing at least a few integer variables. The cut selection process takes into account all of those different measures and computes one single score out of them, then greedily selects the cut with the highest score and removes the ones that are too similar to this one. It iterates further and greedily selects lower scored cuts until a working limit on the number of cuts or the number of cut elements is hit. These limits directly depend on the size of the original problem.
Okay, I hope we selected some good cuts and you will select some good answers in the final quiz of this lecture. Let's go. First question. Which of the following is true? A. There's a unique minimal cover for each knapsack constraint. Or B. A knapsack constraint might have multiple minimal covers. Try to think about the answer. Second question. Clique cuts were originally introduced for A. The knapsack problem. B. The stable set problem. Or C. The traveling salesman problem. And third question. Cut selection addresses the problem when to call cutting plane separators, which cutting plane separators to call, or which of the generated cuts to add to the LP. Little pause. And here we go. For the first question, the right answer is a knapsack constraint might have multiple minimal covers. Second question, clique cuts were originally introduced for the stable set problem. The third question, cut selection addresses the problem which of the generated cuts to add to the LP. Okay, I hope you enjoyed this lecture. Thank you very much for your attention and see you soon for pre-solving. And not to forget about, participate in the cutting plane game. The link is in the description. There will be a prize for the top cutter of CEO at Work 2020. Good luck!